Happy Thursday. All right. So, in terms of announcements, probably later today, if not tomorrow, an announcement will get posted on Learn as to the content on the final term test, which will start a week from tomorrow. That'll get posted to the announcements on Learn as it always does. Other than that, I don't really have anything in terms of announcements. If anyone does have any questions about any of that, feel free to fire it off. Otherwise, we'll just keep going. Okay, so on Tuesday, we were talking about transformations in general, more specifically linear transformations. We saw that transformations were linear. We talked about how to... The test 2 solutions haven't been posted. Well, that's going on my to-do list right now. Post test 4 solutions. When? Probably very shortly after class. Sorry, my apologies. I thought they already had been. Typically, I post them to get auto-released. So I guess I just forgot to do that for this one. My apologies. Thanks for the reminder. All right. Yeah, so on Tuesday, we talked about transformations. We talked about linear transformations. We talked about what a transformation was, what a linear transformation was, how to show something is linear. And then our very last example was this one where we use that it's linear to tell us something about the actual values itself. In other words, we used 3 images. We used what the transformation did to 3 vectors and came to a conclusion about how to do it for a 4th one. So just reminding you what we did, it was right at the end of Thursday, is that we split up 3, -2, 1 just into its I, j, and k components. Then we used properties 1 and 2 to split up the addition or subtraction to factor out the constants. And then we could write everything as a linear combination of the 3 vectors we're given. So my question to you now, because we just ran out of time on Tuesday, is there something special about 3, -2, -1? Or is this something that, in theory, we could do for any vector in R3? And even if it may not necessarily be obvious how, does this seem like something we could do if 3 was a 10 and -2 was a 15 and -1 was pi squared minus 5? Yeah, there's really nothing special about 3, -2, and -1. And so the idea is that we could do this for any vector. In other words, take t, x, y, z. That would be t of xi plus yj. So call this a note. This is technically not part of the question asked. Plus zk. And then we could rewrite this as x times t of 1, 0, 0 plus y times t of 0, 1, 0 plus z times t of 0, 0, 1. So there was nothing special about the 3 numbers we were looking at. We could have done it for any of them. Specifically, this would have been x times 3, 2 plus y times 2, 1 plus z times -2, 1. So instead of getting, instead of getting 3, -2, and technically that's a -1, we could have done it with any x, y, and z's. So in fact, we could have gotten the whole transformation just from those numbers to get 3 times x plus 2 times y minus 2 times z, 2x plus y plus z. So again, what I'm meaning by this note, kind of the big implication of this note, is if we know what the transformation did to these standard vectors, then we can get what, and we know it's linear, then we get what it does for every single vector. So all vectors could be done in terms of just the standard vectors, in this case I, j, and k. And we're going to see how that's going to be useful later on today. All right, any questions about either the original example from Tuesday or this note here that came afterwards? All right. All right, so we're going to start to take this in a, not a different direction, but kind of generalizing the ideas that we're talking about here. So as we mentioned on Tuesday, that any transformation from Rn to Rm could be written in a couple different ways. The way we originally did it, or showed it, kind of down here at the bottom. But also we talked about how you could rewrite it in terms of this other way. So we're just going to use this second way of writing it. Doesn't change what the transformation is. And we can kind of write it in this way. So I'm not claiming this is linear. I'm just saying this could be a transformation, where W1 is kind of this linear combination of the x's, W2 is another combination of the x's, and so on. So this should look somewhat familiar, what we're writing down here. So kind of this W1 in terms of the x's, W2 in terms of the x's, these kind of mini functions. We could write it like this, and if we did, how could we rewrite this system? This should look familiar to something we saw maybe in chapter 1. Yeah, we could rewrite this as matrix multiplication. I'll get to that question in just a second, but we could rewrite this as matrix multiplication. In other words, W, which is W1, W2, if we think of them as column vectors, of course, that could be written as A times x1, x2, all the way to xn. And what is this matrix A? What did we call A? A is not the transformation. And this is not a chapter, what chapter are we in? 4? 1.8? This is something we would have called it back in chapter 1. Yeah, that's just the coefficient matrix. In other words, if we have a transformation that's written in this form, where W1 equals to some constant times x plus some other constant times x2 and so on, if it's written in this form, then we can rewrite it as matrix multiplication. The idea being that, all right, if we write it as matrix multiplication, we know stuff about matrices that we can use here. And so we can use matrix properties to help us, stuff that we did back in chapter 1, and I was showing you all those properties, and you were, loving going through the proofs of those properties, I'm sure. We can use those things to help us now. All right, so my question to you is, would this transformation written in matrix form, does this have to be linear? So if it's linear, let's prove it. If it's not linear, let's come up with a counterexample. So I'll give you a minute or two to think about that as to whether or not this transformation is going to be linear, where W is equal to some matrix multiplied by X. W is a vector. So W is not the transformation. A is a matrix. The transformation is the function. So here, let me show down here at the bottom. So this is the transformation, not A on its own, not the W on its own. The transformation is a times x. That's the function. I mean, we'll always be using t for our transformations. So even if you haven't gone through the entire proof, do you think this transformation is, maybe we can even just get a guess. Do we think this transformation is linear or not linear? Yeah, might not be a surprise that we're guessing that it's linear. I mean, it is called linear transformation, this section. Actually, technically it's not. It's called matrix transformations, but we'll get to that. All right, so let's show that this is linear. So I claim that t is linear. So if we want to show that this is linear, what do we need to do? Left-hand side and right-hand side of what? That's right. We have those two properties. We need to show that those two properties are true. Same thing we did with our specific examples before. Now we're doing it a bit more generally, which makes it sound scarier. But the fact is that we are writing this as matrix multiplication, which means we can take advantage of what we know about matrices in order to do this. That being said, the way we do it, the style, how we set this thing up is the exact same as what we saw before. So property 1. Let U and V just be vectors in Rn. We don't know what they are. It doesn't really matter what they are. We're not giving them specific numbers. And what are we trying to show for property 1? What's property 1 asking us to show? Technically t of that, but that's what it would turn into. T of u plus v. And then t of u plus t of v, and hopefully in the end they're equal to the exact same thing. So, what is the x for this first one? What is the x being put into the transformation? So in this case, x is the thing inside the transformation. So in this case, here is our x, which means that's equal to a times u plus v. Wherever there was an x, we're plugging in whatever was inside the transformation, just like every function notation that you would have done in high school, or you're taking calculus, done in calculus a lot, I'm sure. The idea is, here is the x, we're plugging it in to the x. All right. And the beauty of this is matrix property. So what is this equal to? Using our matrix properties. So that's a times u plus a times v. We don't even need to know what the matrix A is. This was our distributive property. In fact, I think this is the distributive property we proved in class for matrix multiplication back in section 1.3, 4, one of those early sections in the course. All right, what is T of U? Whoops, don't circle with an eraser. What is T of U? That's A times U. What is T of V? A times V. Hey, look, it's the exact same thing. In other words, property 1 is true, and we can do the exact same thing using a different matrix property for property 2. So the nice thing is if we can write our transformation in terms of the things that we already know, matrix multiplication, other types of properties we might already know. If we can write our transformation in terms of these things we already are familiar with, comfortable with, and work with, then these properties are a lot easier to see and to show than they would be for transformations in general. All right, we still have to do property 2, but any questions about how we did property 1? All right, same deal. Let U be some vector in Rn that doesn't matter, and C is some scalar. Technically a real scalar. Then T of C times U. What's T of C times U? And what's the X in this case? Yeah. So if we look at what a transformation is, where does X? So if we're looking at how we're writing the transformation, where does X belong? That's the question. That's the question. If our transformation is matrix multiplication, so the question is, if our transformation is A times X, show that it's linear. So that's part of the question. So we didn't show that T of X equal to A times X. We're saying if it equals A times X, is it linear? So think of it like what the question said to do. All right, so if T of X is equal to A times X, in this case here, what is X? Yeah, X is equal to C times U. So if X is equal to C times U inside the function, then X becomes equal to C times U outside the function. And we get A times CU. And is there a matrix property that allows us to factor out constants? Absolutely there is. And C times T of U would be equal to the exact same thing. Bang. Property 1 is satisfied, property 2 is satisfied, so T is in fact linear. In other words, any matrix transformation is linear. Obviously, the question could also be asked the other way around, is any linear transformation matrix multiplication? And we'll get to the end of that by today. But the idea is if we can write a transformation as matrix multiplication, then that transformation is going to be linear automatically, which is kind of nice. All right, so any transformation of this form has to be linear. And if we do, we'll give it the notation with a little bracket around the T. So if you see a matrix around a T, that's standing for this matrix for the transformation. Assuming that it can be written in this form, and eventually we'll come up to a bigger realization there. All right, so any questions about this idea that if we can write it as matrix multiplication, and for now that's if. If we can write it as matrix multiplication, then it's going to be linear? All right, so here's a question. Here's a transformation. I guess technically I called it linear, but we're actually going to see that it's linear along the way and determine what this standard matrix. So find this matrix A that gives us this matrix multiplication for this transformation. Am I going to teach Math 1700? No, I'm on leave next semester. I will not be teaching next semester. Actually, I haven't taught Math 1700 in a while. I get the Math 1300, 1500s from time to time. Alrighty, so here's our transformation. So what is the coefficient matrix? Well, it's hard to write it all out, so let's take it one row at a time. What's the first row of our coefficient matrix? Because honestly, if we're given it in this way, finding that coefficient matrix, we should be able to get it right from the coefficients there. What's row 2? Assuming I wrote down I wrote it down properly. 4, 1, whoops, that's weird. 4, 1, negative 2, 1. And the last row, five, negative 1, 4, and 0. All right. So honestly, if you're given the transformation with their coefficients like this, then whipping off the matrix shouldn't be that complicated if you're given it in the form that we talked about here. Like if you're given to it in this form, then finding that standard matrix is not overly complicated. So my next question is, same transformation, compute the T of EIs. So E1, E2, E3, E4 are our 4 elementary vectors for R4. Compute what they are either by plugging it into the original transformation or, we wrote the matrix for matrix multiplication. Either way, see if you compute these 4 images, T of these elementary vectors. By the way, just so we're all on the same page, what is E1? What is E1? Yeah. So E1 is equal to 1, 0, 0, 0. E2 is equal to 0, 1, 0, 0, etc. That's what these vectors would be for R4. It is a unit vector, so any elementary vector is a unit vector, but not the other way around. Not every unit vector is an elementary vector. But yeah, I could stick a little hat on these. The last slide. This. I'll find T of the elementary vectors for this one here. Although I'll pop up the OneNote and the transformation will be there as well. All right, so what is T of 1, 0, 0, 0? It's going to be 2, 4, 5. How about the second one? So again, this is not anything new. There's a lot more zeros, which make it a little bit easier, but this is exactly what we did to start this entire section, which is, all right, if we want to find out 1, 0, 0, 0, that just says plug in ones for every x1. So this would say x1 equals 1, x2 equals 0, x3 equals 0, x4 equals 0. And so there's a 1, but all of these are 0, 0, 0. Everything that's not an x1 turns out to be 0. And the x1s are all equal to 1s. So we're getting 2, 4, 5. Similarly for all the other ones, what's the third one? T of E1, I should just, or E3. I should just write E3. Yeah. Yeah, so that's going to be 4, negative 2, 4. And I'm squeezing this in the bottom because I don't want to lose what's on the screen. 5, 1, and 0. And my next question was, on my slide, has already been answered. What does it look like is happening? T of these elementary vectors, looking at the standard matrix, what does it look like is happening? Yeah, it's just the columns. And, I mean, in theory, that could be a coincidence, although it would be a pretty big coincidence. But hopefully it makes perfect sense why this is happening. Why did this become a 2? So in terms of why this happens, if we expect it to always happen, then we better have a reason for it. Why did that become a 2? It became a 2 not because of 5 things where things magically canceled off, but because we had zeros, all 3 of these terms became a 0, and the only term that survived was 2x1, and since x1 was equal to 1, the only thing that survives is the coefficient of x1. So the fact that we're getting 2 is because 2 is the coefficient of x1. Same thing with the 4 in the second component, same thing with the rest of them. So this is no coincidence. This is happening for a good reason. And same thing for all the other ones. In other words, these elementary vectors are very special and helpful for us. In general, the matrix for our transformation, the first column is going to be what we get when we plug in the first standard vector into the transformation. Same thing for the second one. All the way to the n, we have n columns. So this is how we can find our standard matrix. Now, obviously, if we're given the components, then it's just a coefficient matrix. This would be overkill. But we're going to find this second thing to be helpful in a situation where we're not given the components. And we'll see an example of that in just a minute. All right, any questions about kind of these ideas where if we plug in our standard elementary vectors, we end up just getting the columns of our matrix? All right. So let's give this one here a try. So here's a transformation. It's t of x is equal to a cross product. 1, 2, 3, cross with x. First of all, verify it's linear, and then second of all, see if you can find that standard matrix. So all this standard matrix stuff only works for linear transformations. If it's not linear, then everything we did gets thrown out the window. Yeah, cross product of x. Probably using x for the vector might not have been the best plan for me. But one is curvy. That's something. Can I go to the last slide? I think I just wrote down what the function was, but here. Yeah. So t is the operator on R3 defined by t of x is equal to 1, 2, 3 cross x. Yeah. Yeah, so the big idea here is that any transformation can be written in terms of one of these matrices. Any linear transformation can be written in terms of one of these matrices, which is kind of nice because we can always take advantage of these matrix properties, even if the transformation doesn't look like a matrix. All right, so in the question, I didn't write this on the OneNote, but in the question, I said, let T be the operator. All of a sudden, I'm using this new word, so I better make sure everyone's aware of what this word is. So what is the difference between a linear transformation and a linear operator? It's just a terminology thing. It doesn't change what we do. What is an operator as opposed to a transformation? It's actually wrapped up in the English meaning of the words. Operator for operation versus transforming something. And I'm not even 100% sure I defined this in the video, so in the pre-lecture video. Yeah. So an operation is like adding, subtracting, multiplying, dividing, in this case, kind of multiplying, where what you get out of it is the same type of object you get into it. You add two numbers together, you get a number. You subtract two numbers, you get a number. Multiplying, dividing most of the time, etc. So an operator would say what two things are the same. Yeah. Ooh, there's some fancy words. Yeah, so the domain, in this case R3, and the codomain, the space where the outputs live, are the same. So if we're ever using the word operator, then that would say the domain and the codomain have to be the same. What would that mean for the standard matrix if the domain and the codomain were the same? Not that we really need this. Yeah, it would mean that it's square. So an operator is is an example of a transformation, but the domain and codomain are the same. Whereas a transformation can change it from one dimension to another. All right, anyway, so we want to show this thing as linear. Same way we did it before. Need to show properties 1 and 2. Here's our transformation right here. We need to let U and V be some stuff in R3. That's the worst 3 ever. So we want to find T of U plus V. So how can we, like I said, if we can take advantage of other things we know, we want to take advantage of those things. So is there anything we can take advantage of? Is that an arrow beside R3? Oh no, this is the let U and V be something in R3. Yeah, my handwriting is typically I need to focus to keep my handwriting legible. Sometimes I lose focus. So is there any properties that we can use that are going to be helpful? In the same way we used matrix properties before, are there any properties we can use that might be helpful to do this as opposed to having to go U1, U2, U3 and make a mess of it? Are there any cross product properties that we have that might be useful? I know the cross product kind of got unfortunate with some of their properties, but is there any cross product properties we can use? Let me ask my question again. Is there any cross product properties that we might be able to use? Yeah, that second one is certainly going to be helpful. What other one might be helpful, maybe for property 2? I don't think the last one's going to be helpful because I don't know if we're going to take the cross product twice. Yeah, that fourth one that deals with scalar multiples. That one might be helpful as well. In other words, T of U plus V, our X, as always in property 1, is equal to U plus V. And that second property of cross products says that this is equal to 1, 2, 3 crossed with U plus 1, 2, 3 crossed with V. The first one being T of U, the second one being T of V. So again, the idea, same as matrix multiplication. The idea is if we can write our transformation, or in this case, if we're given our transformation in terms of things we know. Matrix multiplication, we have properties for cross products. We have properties for dot products. We have properties for. So if we can write our transformation in terms of these things, we can take advantage of those properties to know immediately or almost immediately that they're in fact linear. All right, so that's property 1. Any questions about property numero uno? Yeah, so we used, come on, highlight for me. We used this second one right here in this step right there. So the one that went from the first thing in that quasi-circle sort of ellipse to the second one, we use that second cross product property. All right, for the second property, now X is equal to C times U, as it always is for the second property. Now we're taking advantage of the fourth one, where the K, kind of the first and last pieces of the fourth one, where the K can be factored straight out in front. One, two, three, cross with U. C times T of U. So T is in fact linear. Satisfies the adding property, satisfies the constant multiple property, technically called being homogeneous, and therefore we have that t is in fact linear. And the moment we know it's linear, then we can use all of those ideas we've been developing between the second half of Tuesday and so far today. All right, so any questions about why the cross product is linear? All right, so we actually have a couple options here. So we do have a couple options in terms of finding the standard matrix. So any ideas how we can find the standard matrix? Kind of talked about two different possibilities for this, both of which we've talked about today. So what were our two methods? Yeah. Well, the first one we saw is find components. So one, find components and find the coefficient matrix. So that's what we did for our first example. Our first example was let t of x, and we got the whole string of components. In that case, we could immediately get our answer by finding the coefficient matrix. Unfortunately, in this example, we don't have that. In this example, we're not given the components. We're given a different way of looking at the function in terms of the cross product, which means we'd have to first find the components in order to do that, using x1, x2, and x3, and find the components, and that could be quite a bit of a mess. It's doable, but it could be a mess. And the second option, as some people have been saying in the chat, use the elementary vectors. In this case, personally, I think that would be easier because then we only have to take the cross product with nice elementary vectors as opposed to some general mess of x1, x2, and x3. The downside is you got to do it 3 times, but at least they're very nice vectors to work with. All right, so those are our two methods. Let's try number 2 because we've already tried number 1. So we want to find t of 1, 0, 0. So how do we find t of 1, 0, 0? This will be our column 1. How do we find t of 1, 0, 0? Exactly. Plug in 1, 0, 0 for x. That's t. That's 1, 2, 3 cross with 0, 0, 0. ijk, 1, 2, 3, 1, 0, 0. So that's going to be 0i minus, is that 1, 0 minus 3j. Cross products aren't new to us by this point. And then plus negative 2k. In other words, that's 0, 3, negative 2. So there's our first column. It's 0, 3, negative 2. And we'll just do this with the other elementary vectors as well. So there's 3 little cross products to take, but all of them are fairly straightforward because 3 of them are 0, or 2 of the 3 are zeros. In fact, instead of expanding along row 1, what could we do instead? Yeah, we could expand along row 3. So that's 0 minus 1 times, what's that, 3i minus k plus 0. In other words, that's negative 3i plus k if we expand it along row 3, as opposed to expanding along row 1. That's negative 3, 0, 1. And lastly, t of 0, 0, 1. We could expand along row 3 again. And get 0 minus 0 plus 1. And then what's that? 2i minus j. So the beauty of this is we don't need the general transformation in order to find the standard matrix. We can just find it with 3 really nice vectors in order to get our first, second, and third columns. So the first column is 0, 3, negative 2. The second column is negative 3, 0, and 1. And the last column is 2, negative 1, and 0. We get this not really symmetric matrix, but it kind of looks somewhat symmetric and kind of weird. All right. So any questions about how we can find the matrix of this transformation, the standard matrix, from our elementary vectors? Yeah, we haven't defined this. This would actually be called skewed symmetric. In no way is that needed for this question, of course. But yeah, this would be an example of a matrix where A transpose is equal to negative A, which has some nice properties, none of which we're really going to explore as part of this example. Right. So the nice thing that after we find the matrix is we can start to use this matrix. So here's a couple more questions. So let's use t to compute 3, 2, negative 1. And then also use t to see if we can find all the x's such that t of x is equal to the 0 vector. So again, both very standard type questions that we can use the standard matrix to help us do. I'll give you a couple minutes to give those a try. All right, so obviously we could find t of 3, 2, negative 1 by plugging in the vector 3, 2, negative 1. So the point of the finding t of 3, 2, negative 1 is how can we use the standard matrix to find it? Like we went to this work of finding the standard matrix. So how can we use it? Yeah, just take the matrix. And now, once you've found the standard matrix, any transformation question now becomes a matrix question. And we're going to see that not only in this section and sections, we're going to see it in chapter 5 as well. Is the standard matrix is this bridge between transformation functions and matrix operations. So anything we can do with a matrix, we tend to start being able to do with a transformation as well. All right, so now it's just matrix multiplication. What's that? Negative 6 minus 2 is negative 8. 9 plus 1 is 10. Negative 6 plus 2 is negative 4. And we're done. Hopefully. Negative 24. Yep. There we go. And so now, if we have this standard matrix, then any transformation question turns into a matrix multiplication question. So you'll note here we're flip-flopping between writing it as a vector and writing it as a column matrix. As I said right from the beginning when we started this, that's something we're just going to do. That we're just, whether we're writing it as a column matrix or writing it in normal vector format, we're talking about the same thing. All right. So any questions about how we computed t of 3, 2, negative 1 using matrix multiplication? All right. As for the second question, how do we use matrix stuff in order to solve? You don't need to know this word, but just in case you read this word, for the kernel of t. In other words, the set of all x, where t of x is equal to 0. So what can we do in order to solve that? Well, forget I said the word kernel. We're not having popcorn or anything. Insert bad dad joke here. Yeah. In other words, for the second one, we're going to solve x is equal to 0. Again, t of x and matrix multiplication are the exact same thing. So we're really solving a matrix equation. And how do we solve? Well, any matrix equation is a system. So how do we solve this system of equations? I think we have about 85 different ways. So what options do we have in order to solve this? Row operations was the first thing we did. Absolutely. Nice thing about row operations is it works every time. Works every time. Nothing special needs to be known about the matrix. That being said, if we do know more about the matrix, if the standard matrix was invertible, we could multiply by the inverse because it is square. If we could use Cramer's rule in theory if the determinant was not equal to 0. But the nice thing is row operations do work every single time. We don't need to know in advance whether or not the determinant is 0. And in fact, if you do this and find the determinant, you'll actually notice the determinant is 0, in which case no other methods but row operations are going to help us. All right, could get creative here. Let's swap row 1 and row 2 in order to get a non-zero number. I'll try not to focus too much on the row operations here because that's not the new stuff. The new thing, the thing I really want you to get out of this is the fact that anything with a linear transformation, any question about them usually can be reduced down to something about matrices. All right. We can maybe avoid fractions as long as possible. You could divide row 1 by 3. That would work. But we could also add row 3 and get a leading one without involving fractions, at least at this point. Row 3 is row 3 plus 2 row 1. As always, my row operations and yours might not be the same, and that's okay. 0, 3, -2, 0. Can't avoid fractions now. Row 2 is row 2 divided by -3. 1, 1, -1, 0, 1, -2/3. And then row 1 minus row 2. And row 3 minus 3 row 2. We get 1, 0, -1/3, 0, 0, 1, -2/3, 0, 0, 0, 0, 0. In other words, x3 is equal to t. x2 minus 2/3 x3 is equal to 0, which says x2 is equal to 2/3 t. And x1 is equal to 1/3 x3, which is 1/3 t. In other words, x is equal to 1/3 t, 2/3 t, t for any t in the real numbers. Great. So here we go. And we've managed to solve for all x, but even though it was in a completely different context, it was a transformation question about a geometric question, it turned into row operations on a system of equations. All right. Any questions about this or any of this linear transformation itself? Because this is kind of the end of section 1.8. All right, you don't need to know this, but kind of an interesting little side note. What would happen if we factored out t over 3 out of that vector? This is a bit of an aside, but what would we get if we factored t over 3 out of this vector? We get 1, 2, 3. I claim that this makes perfect sense that we're getting 1, 2, 3. Why should we be getting 1, 2, 3 for an answer to this question? Times some multiple. I mean, a bit more specific. These x's, again, think of it geometrically. X is some multiple of 1, 2, 3. What does that mean geometrically? X is some multiple of 1, 2, 3. So what does that mean geometrically? It's a scalar multiple, which means those vectors are parallel. So what is this saying? This says that the only things that are going to be whose cross product with 1, 2, 3 is going to give us 0 are the vectors parallel to 1, 2, 3. That doesn't seem like the first time we've said that. So technically, I guess this is kind of verifying what we already knew. The only thing, the cross product that crosses with a vector to give you 0 are things that are parallel to that vector. All right, never mind. All right, so that's end of section 1.8. So we're going to technically now we're moving on to 4.9, which is what I like to call the section of 1,000 examples. So 1.8 was all about matrix transformations, linear transformations, what makes them linear, the stuff we can do with them. And section 4.9 is just 100,000 examples of these linear transformations, these linear operators. So we're just going to basically, between today and Tuesday, going to be going through them because I don't really know how to make it more exciting. All right, anyway, so the first one being the zero transformation, the shocking transformation that t of x, I should have put that in a bracket, t of x is equal to 0 for all x. So without writing anything down, can anyone give me a quick reason why this is a linear transformation and what the standard matrix is going to be? Because quite frankly, this one is boring. Why is this linear? Why are these properties t of u plus v equals to t of u plus t of v? Or maybe even a more natural question is, what would the standard matrix have to be? Yeah. Yeah, the standard matrix is going to be the zero vector. So our zero transformation says t of x is equal to 0 for all x. In other words, what is t of E1? Is 0 a number or a vector? Did I forget it in my thing? No, I didn't forget it. In this course, I want the vectors there because the vector notation there because I want to make sure it's clear the distinction between when we're using numbers, aka like in a dot product, or when we're using vectors like what we're seeing here. All right, so the first column is t of E1. What's t of E1? I'll get there. What's t of E1? So our transformation is everything becomes 0. So what's t of E1? 0. What's t of E2? 0, etc. In other words, the standard matrix is the zero matrix. This isn't quite perfect. We'll fix it up a little bit, but yeah. I mean, the zero transformation is the easiest one because everything just turns into 0, which means every entry in our coefficient matrix is 0. All right. I guess a zero matrix isn't quite specific enough, though. What size? What size of matrix is this zero matrix? Certainly depends. Some people saying n by m, some people saying m by n. Oh no. Which one is it? M by n or n by m? Yeah, that's honestly the only real tricky thing about this is what is the size. Doesn't have to be square. Doesn't have to be square. All right, let's go back to this. Kind of in general, looking at our stuff here. If our domain is Rn and our codomain is Rm, then what's the size of our matrix? How many columns does it have? And how many rows does it have? The n gives us the number of what, and the m gives us the number of other what. Yeah, it's the codomain by the domain. Right. Another way of thinking about it is if our domain is Rn, if our domain is Rn, then we have n elementary vectors, and they go in the columns. They don't go in the rows. They go in the columns. And so it is an m by n, not an n by m. In fact, because we usually write m by n, that's why we tend to write we tend to do Rn for the domain and Rm for the codomain, is because then our matrix would be m by n. All right, so real boring, zero transformation, 0 for our standard matrix. All right. Oh, why is it linear? Well, 2 reasons. Number 1, everything becomes 0. But the idea of why it's linear is because, well, actually, good question. And even though I don't usually refer to the private questions, we never really did answer this. So why is it linear? First of all, we can write it as matrix multiplication, so there's a reason right there. But second reason is, what is T of u plus V? 0. What is T of u plus T of V? 0. Yeah. Because everything turns out to be 0. T of Cu is 0. C times T of u is 0. Everything is 0. And hence, since everything is 0, everything is equal. And that's kind of why it's linear. All right. or I guess technically operator. Identity operator. T of x is equal to x. Not particularly exciting. Again, let's give a quick reason why it's linear. But also, again, what would the standard matrix be? What matrix times x always gives us x? That's right. So in other words, we could justify that it's linear in a couple different ways. T of x is equal to I times x, which is equal to x. So the standard matrix is just the identity, and it's linear. You could either show the properties, or how could we justify that it's linear without showing the properties? Kind of had a backdoor way into doing this. How could we show it's linear without showing the properties? So not using the definition, but using a theorem. Right, since it can be written as matrix multiplication. So if the transformation can be written as matrix multiplication, then we know it's linear automatically. We showed that any matrix transformation is linear. So linear since it can be written as matrix multiplication. Beautiful. So the identity transformation, pretty boring one, but it is. All right, so from here on in, we're going to be really getting into the geometry of what we're trying to accomplish. So every transformation from here on in, and technically the last two also works, our focus is going to be on the geometry, what it means for us geometrically. So in terms of the identity transformation, what does the identity transformation do to a vector? Absolutely nothing. So pretend I drew those in the same way. So the identity transformation does nothing to the vector. So that's going to be our focus throughout all of these examples that we're working on, is what does the transformation do to the vector? There's the geometry, and what is the standard matrix, which what helps us with the algebra. And that's kind of, since the beginning of the course, that's what's been our focus. Geometric to use it, algebra to calculate. All right. So here's another one. Let's ignore the quick reason why it's linear. So if t of x is equal to k times x, the quick reason why it's linear is the same as we had before. So three things. Number one, what is the standard matrix? What does this do geometrically? And there's some names down here at the bottom that we'll give to it. So if t of x is equal to k times x, what is the standard matrix? And what does the operator do geometrically? So geometrically speaking, it changes the length by the factor of k if k is positive. If k is positive, it just changes it. The length times k. If k is negative, because what happens if k is negative? It goes in the opposite direction. Yeah. So if k is positive, we kind of, honestly, if k is negative, we can think of it as a reflection. We could also think of it as a rotation. We'll talk about both of those on Tuesday. So opposite direction and length times the absolute value of k. All right. So that's what it means geometrically. If k is 0, then it's the 0 transformation. And we're back to where we started with. Technically, if k is 1, it's the identity transformation. What would be the standard matrix? Yeah. K times the identity. Again, you could ask yourself, what happens to the elementary vector? So 1, 0, 0 would become k, 0, 0. So the first column is k, 0, 0. Do the same thing with the other ones. The other way, and this is actually going to be something that's going to be useful later in chapter 5, is we have a constant multiple times x. How could I take a constant multiple times x and write it as a matrix times x? Again, this isn't necessary for this question, but it's going to be helpful later. How can we write a constant multiple times x and rewrite it as matrix multiplication, because k is not a matrix? How could we write that? Yeah, that would be k times I x. And then we can just use that it's associative. So that's overkill for this question. But this skill of taking scalar multiplication and rewriting it as matrix multiplication is something that we're going to use in Chapter 5. So, for this constant multiple transformation, technically an operator, because it doesn't change the space, is geometrically multiplying by k, maybe flipping it if k is negative, and the standard matrix is k times the identity. And in terms of terminology, this is called a dilation. If k is bigger than 1, it makes it bigger. And it's a contraction because if it makes it smaller. So if k is bigger than 1, it's dilation. So if you're seeing in the textbook dilating by a factor of 3, that's what it means. If it says contracting by a factor of a half, then that just means k is equal to a half. All right, anyway, that's it for today. We've already gone a few minutes over. So on Tuesday, the bulk of Tuesday is going to be talking about a couple more a few more different types of geometric transformations, reflections, rotations, projections. And that's where we'll go with it. If you have any questions, let me know. If not, that's it for today. Have a good weekend.